Alright, the last section in Chapter 12 is about how you can transform data to achieve linearity. So sometimes when you're looking at data, it's not linear. So here's data. So we have the country's under 5 child mortality rate per 1,000 live births, and then here's the income. And so if we type all those in and you look at a scatter plot, you would see a strong negative nonlinear relationship. It actually looks like this. So it's not linear. So I can use like power models or log models instead of a linear regression model, but sometimes I can just also transform the data and still use my familiar linear regression. So what we're going to do here is transform the data. So what I'm going to do is I am going to take, instead of using the x variable, under 5 mortality rate, we're going to do 1 over that, and then still use the y as it is. And if we do that, we see this scatter plot, which creates a strong linear relationship. I could flip it though, and I could take the x and then I could do 1 over the y, and I could look at that scatter plot. So that's what they've done here. So here is 1 over the under 5 child mortality rate with the income. There's the output. There's the residual plot. And then here is the under 5, so the x is left as it is, and then they took 1 over the y variable. There's this output, there's the residual plot. Alright, so then for both of those transformations, I could create a different regression line. So for the first one, so when the x is transformed by taking the reciprocal, there's my intercept, there's my slope. So then what I wrote here, so I still have y hat as my predicted income, there's my intercept, there's my slope, and then instead of x, I have 1 over x because the data has been transformed. In transformation 2, I have there's my intercept, there's my slope, and now I have 1 over y, and I have the hat over all of that, and then I have the x left as it is. I can plug in a number into each of those equations, so 20.3, I can plug it in there, I can plug it in here, and get 2 different answers. Each of these graphs have different r squareds, so just looking at the computer output, there's the r squared for the x over 1 transformation, or 1 over x, sorry, and here's the r squared for the 1 over y. And you can see I kind of talked about the reciprocal there when I was talking about the transformation. You could also see from this that probably the second transformation is a little bit better since the r squared is higher, so it's probably preferable to transform the income as opposed to using the under 5 being transformed. But what you can see here is that, so I took data that when I just plotted it as x and y data, it didn't look very linear, but I transformed, I changed one of the variables, and now I have a linear relationship. So I can go back and use what I am familiar with. Alright, so there are two types of transformations that you're going to see, and this is just kind of a lot of explanation for it, but basically you're either going to see one that things are being raised to a power, so like in the last one we were taking things to the power of -1, or you're going to see that things are having an exponential relationship. So in this example right here, so here's an example about M&Ms. You can go back and read any of that, read your book if you want to understand a little bit more. I'm just trying to get to the main points. So there's an example with M&Ms. So he was dumping them out, and he was eating all the ones that had an M on top. So after the first dump, there was 30 with M on top. Then he put them back in. After the second dump, there was 13, and then so on. And then he graphs this, and you see here that there's like an exponential relationship. So, and since we also know that the number of m's are supposed to kind of probably, we would expect the likelihood of an m showing up or not showing up would be about 50-50. So it's going to be cut in half after each course or each dump of his bag. So we think an exponential model will be appropriate here. So to do the exponential model, what they do is they take the natural log of the number of M&Ms remaining, and they have the natural log, so you can always figure out what transformation was done by looking at a graph. So the natural log of the remaining versus the course, so the bag dump that you're on. And now you can see there's a strong negative linear relationship. Here's the mini-tab output. So they took the natural log of the M&M, so that's the y. And there's the slope, there's the intercept. You can use that to do a prediction. So now if I'm plugging in 0 here for the prediction, so that's going to be 0. I have that number right here. So I need to take both sides to the e, I don't know, and then that's what I would get there for the number of original bags. When I look at the residual, so this is the residual plot of the course versus the natural log, and I can see that the residuals are uniformly scattered, so there is a linear model is appropriate. All right, here is the important thing to know. You will not be asked to do a transformation on the AP test. You will not have to figure out what transformation to do. They may give you a graph like this example right here and say which transformation is better. They may give you outputs. They might tell you like the natural log was done and then is a linear model appropriate now based after the transformation, but they will not expect you to figure out what transformation to do. You just might have to answer some questions about it. So the big thing I would just know is that realize that sometimes data is transformed, so there's a linear fit. And then just know that you just rewrite your equations slightly differently based on that transformation. So the natural log, or maybe there's a power or something like that. That is it.